Assalamu alaikum. My name is Asma Bashar. My student ID is 210050670004. And today I will present a detailed explanation on flexible electronics, which is a revolutionary branch of modern technology that is reshaping the future of wearable devices, healthcare, smart textiles, and much more. Introduction to flexible electronics. Let's begin with the definition. Flexible electronics, also called flex circuits or soft electronics, are devices and circuits that are manufactured on flexible substrates. These substrates allow the electronics to be bent, folded, twisted, or even stretched without losing their functionality. Now, let's look at the key characteristics. They have high flexibility and mechanical resilience, making them durable under movement. They are lightweight and have ultra-thin form factors, which is perfect for integration into compact systems. And most importantly, they can conform to non-flat or curved surfaces, making them ideal for wearable or body-mounted devices. The significance of this technology lies in its ability to seamlessly integrate with the human body. Smart clothing and curved electronic devices. Some common examples include wearable health monitoring devices, rollable and foldable displays like modern smartphones, skin mounted biosensors, flexible solar cells, and flexible RFID tags. Evolution of historical background. Now let's look at the evolution of flexible electronics. In the 1960s, the journey started with the development of thin film transistors on flexible materials. During the 1980s and 1990s, organic electronics and polymer-based semiconductors began to grow in popularity. In the early 20s or 2000s, flexible printed circuits and electronic paper were commercialized. By the 2010, flexible OLED displays and wearable tech entered the market. Today, and looking toward the future, flexible electronics are becoming increasingly integrated into healthcare, wearable computing, biodegradable devices, and smart packaging. Key components of flexible electronics. Flexible electronics are composed of four main components. Substrates. These are the flexible based materials. Polyimide. It's widely used due to its excellent thermal stability and flexibility. PET and PEN, which are polyethylene terephthalate and polyethylene naphthalate. Common in consumer electronics, textiles, and paper. These are used in the wearable and disposable devices. Second one is conductors. These materials carry the electric current. Silver nanowires and nanoparticle inks are used for high conductivity. Carbon-based materials such as graphene and carbon nanotubes provide both flexibility and electrical performance. Conductive polymers like PEDOT, PSS are also used. Third one is semiconductors. They control the electrical behavior. Organic materials like pentacene and P3HT. Oxide semiconductors such as IGZO, which is indium gallium zinc oxide. Amorphous silicon is also sometimes used. Encapsulation layers. These protect the electronics. Materials like parylene, epoxy resins, and barrier films are used to protect the circuits from moisture, oxygen, and mechanical stress. Fabrication techniques. Let's talk about the flexible electronics are actually made. There are multiple fabrication techniques including printing based techniques, inkjet printing, a digital and contactless method perfect for prototypes, screen painting used for mass production of conductive layers, gravure and flexographic printing ideal for large scale production used in the roll to roll methods, photolithography modified for low temperature processes to suit flexible substrates enables micro and nano scale patterning, transfer printing transfers micro components from rigid to flexible substrates using elastomeric stamps. Laser processing used for precise cutting and shaping of films and layers. Working principle: flexible electronics work by depositing conductive tracks and active components on flexible substrates. These circuits are designed to maintain performance even when bent or stretched. The design often including zigzag or serpentine interconnects which reduce mechanical strain. Layered structures help to isolate sensitive components from stress. These systems also integrate sensors to detect signals, actuators to perform functions, displays and communication modules, even power sources like flexible batteries and supercapacitors. Advantages: flexible electronics offer a wide range of advantages. Mechanical flexibility: they can be attached to or embedded in most any shape. Portability: their lightweight and compact nature makes them ideal for wearable and implantable systems. Durability: they are resistant to vibrations, shocks, and repeated bending. Cost-effective manufacturing techniques like roll-to-roll printing reduce production cost. Design freedom: you can create innovation designs like foldable phones or smart clothing. Applications: there are many practical applications of flexible electronics across industries. Healthcare and biomedicine: smart bandages that monitor wounds, wearable patches for ECG, hydration, and body temperatures, implantable flexible biosensors for continuous monitoring, consumer electronics, foldable smartphones and tablets, rollable e-paper, OLED displays, and smart glasses. Energy sector: flexible solar cells in clothing and backpacks, printable batteries, and energy harvesting system. IoT and smart packaging: RFID tags, RFID tags or NFC system for smart product tracking. Smart labels to monitor freshness or temperature. Defense and aerospace: lightweight sensors are for aircraft, wearable communication devices for military use. Challenges: despite the potential, flexible electronics face some major challenges. Material limitations: organic semiconductors have lower mobility and shorter operational life. Conductive inks might degrade or peel off when stressed. Manufacturing complexity: aligning layers accurately on flexible materials is hard. Multi-layer printing often leads to defect if not controlled. Environmental stability: these devices are vulnerable to moisture and oxygen. This requires strong encapsulation layers. Energy integration: it's difficult to develop thin, flexible power source that last long and harvest energy efficiently. Scalability: most current processes are limited to lab scale. There are the lack of standardized testing for flexible electronics. Future trends and innovations. Finally, let's explore the exciting future trends in this field. Self-healing materials, these can repair themselves after damage, restoring both shape and function. Biodegradable electronics, ideal for temporary medical implants or eco-friendly sensors. Stretchable and transparent devices, great for smart contact lenses, soft robotics, and next generation displays. AI integrated wearables, devices that can learn from data and give personalized feedback for health. Neuromorphic or brain machine interfaces, electronics that mimic brain signals, helping control prosthetic limbs or robotic systems using thought signals. Thank you.